couple of other types of problems involving probability. Okay. Not necessarily any new probability events, just some sort of scenarios that you should be aware of. Okay, because the basic ones that we've talked about, there's three of them. And they kind of break down like this. I don't know if you want to write this somewhere, but the probability of one event or another happening will be the probability of A plus the probability of B if they are mutually exclusive. That means they have nothing in common. However, it's going to be this if they aren't. This is if they're not mutually exclusive. This means we have to subtract the overlap. So there's kind of two situations where you use the addition rule. So this would be considered the addition rule. Mutually exclusive, not mutually exclusive. For multiplication rule, oh, that's fine. Yeah. If we want the probability of one event and another event happening, again, there's two situations, whether they're, whether they're independent or not. So if they're independent, and this is what we're going to look at today, we just simply multiply the two probabilities together. This is if they're independent. If they're not independent, this is where we have to multiply the two probabilities together, but the second probability will be conditional on the first event. It's still the same multiplication. Okay. So this is not independent. Finally, our conditional probabilities, we divide. What do we divide? The probability of the two events happening together divided by the probability of the second event. Okay? That's really what the majority of these questions break down to. You're going to be adding or subtracting or multiplying. The challenge comes in interpreting the question and understanding, okay, which one is this here? Is it one where I have to add? Is it using the word or? Is it one where it's using the word and I have to multiply? Do I see the word given? Given means conditional probability, and I'm going to be dividing. Roshni. No, we talked about that yesterday, that they were not the same. Yes, not mutually exclusive. Okay, so just sort of keep that in mind. That's kind of a good guide to have. I want to make, let's see, which ones will you always get? Let me just formula sheet. Yeah, those are the ones you're going to get. You're going to get the addition rule, and you're going to get condition. So you'll get the first and third ones. Okay. But we can find the middle one, the P, A, and or B, by manipulating this formula. How do you get P, A, and B by itself? Just multiply this by this. Okay. Okay. Now, and we'll first start about successive events and independent events, which means we don't have to worry about conditional probability. Okay, which means we're going to be multiplying too. So events are successive if one happens right after the other. What did I have here? What did I say? Oh, repeated process. Repeated process. You're doing something several times. You're rolling a die several times. You're flipping a coin several times. Okay? And remember, they're independent if knowing the event of outcome of one event does not affect the probability of another event. Doesn't affect, doesn't influence. Okay, so you flip a coin, what's the probability of getting heads 5 times in a row? So that means you're getting heads and heads and heads and heads and heads, not or. So that tells me multiplication. So if we used a tree diagram, it would look something like this. Okay? We'd have heads or tails, and it'd be 0.5 and 0.5. And then it would go like this again, heads or tails, heads or tails, heads or tails, and heads or tails. But we don't really need a tree diagram. I just drew one branch because we want to know 5 heads in a row. And these are independent. They don't change because a coin doesn't have a memory. So how would we find the probability of 5 heads? Right. So it would be, I mean, if we use probability notation, it would be heads and heads, and heads, and heads, and heads, or 0.5 times 0.5 times dot 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 times 0.5, or what's the simplest way to say it? 0.5 to the 5th. Might as well use exponents. That's what they're there for. Save you some time. And what does that give us? Okay, so we can round it to 0.03. Let's say approximately. So about 3%, a little over 3%. So, I mean, you can use a tree diagram in this situation, but you don't have to. All right, I think we're all familiar with the free throw in basketball. One of the best free throw shooters is Steph Curry. He makes 90.6% of the free throws he attempts. Assume each free throw attempt is independent. That's important. What's the probability he makes 6 in a row? How would you find that? Probability 6 in a row. And we know the probability each time. Anna? Yes, but remember, that's a decimal. Like that. And that gives us approximately 0.553 if we wanted to change it to percent. We get 55.3%. Okay. All right. So many times he's fouled in a 3-point attempt situation, which means you get 3 free throws. Okay. When he takes those 3, what's the probability he makes the first 2 but misses the third one? Makes first 2. Misses last. Well, what's the probability he makes the first one? 90.6%, but let's change it to decimal. We're going to 0.906. What's the probability he makes the second one? So the probability that he makes the first and the second is this. And misses the third. Times whatever 1 minus this is. What is it? 0.094. Because they're successive events, so we multiply them together. And they're independent, so I don't have to worry about conditioning. So when I multiply those 3 values together, I'm going to get approximately 0.077, or about 7.7%. So that's successive events. Next thing, situations that involving the phrase at least one. So again, he makes 90.6% of his free throws. Assume each of his free throws are independent again, in order to do this the way we've been doing it. What's the probability that he makes at least one of his next 4 free throws? That's a little trickier, because it could be the first one he misses, right? It could be the second one. It could be the third one. It could be the fourth one. Well, that's a lot of calculating to do. Okay. Fortunately, there's a way around it. To find the probability of at least one, we can find the probability that he makes none of them. That's pretty easy. And subtract that from what? What do these 2 add up to? Always 1, right? Because if he's making at least 1, that's a whole bunch of probabilities. The only other possible situation is none. So that's how I calculate at least 1. So when you see that phrase at least, think this, because it's much quicker. Because what's the probability that he makes none? It's 0.094 to the 4th, isn't it? because makes none is misses and misses and misses and misses. So 0.094 times 4 times. And when you calculate that, you're going to get approximately 0. You're going to get a very high probability. 0.09, and I kept writing nines because if I didn't, I'd have to round to 1, and I didn't want to do that. Which is about 99.992%. So it's highly likely that he's going to make at least 1, because it's very unlikely that he misses all 4 because his probability is so high. So that number makes sense. Yeah. Yeah, when you're that close, keep expressing decimal places because you don't want to round it to 1. Because there is a small chance that he doesn't make it, that he misses all. Okay? So again, I just 1 minus probability of none. Finally, and I talked a little bit about this yesterday when I talked about the deck of cards, about independent versus not independent. So you have a jar with 12 blue marbles and 8 red marbles. Imagine you sample marbles without replacement. So you pull a marble out without looking, you don't put it back in, and then you draw the second one, the next, and then you draw the third one. So what's the probability that you're going to draw blue, then red, then blue? Here we're going to use fractions. So you just started. How many marbles are in the jar? 20. What's the probability of drawing a blue? 4. You do not put that blue one back in. How many marbles are now in the jar? 19. How many are? So 8 out of 19. You do not put that red one back in the jar. How many in total? How many are blue? 11, because 1 was already out. And if I want to find blue and then red and then blue, not or, I multiply. And then you can just go to decimal and you'll be approximately 0.54. Yeah. Yes. Yes. I'm trying to think if you'll ever see that. That's why I hesitated. Okay. Before we close this down, let's let me throw a couple of examples at you. I'm going to make you think. What's the probability of A or B? Does anybody want to offer a different solution? Exactly. Are they mutually exclusive? I never told you that. So you can't just add them. Okay? However, if I added this, this is telling you that they're not mutually exclusive. So therefore, what would be the probability of A or B? It would be 0.4 plus 0.2 minus 0.1, which would be 0.5.
Yeah.
Okay. What if I, what if I erase this and told you that they were independent? What is the probability of A and B? Which is 0.08. So you gotta, my point is, look at the wording carefully. All right. Worked out nicely. So, I don't know, whatever X and Y represent, chromosomes or something. What's the probability of selecting a Y? I asked for the probability. Probability can't be greater than 1, so 25%. Isn't it out of the total? 25 over 40. Yeah. Okay. What's the probability of selecting an X and Y? 17. What's the probability of selecting an X for a Y? 34, because you just add these three up. What is the probability of this? I'm not going to say what it means. 14 over 40. Because as long as it's not X, so we don't include these, we add these two up and we put it on 40. Good. Okay. What is the probability of X given? 17 out of 25. Because remember, it's both of these, which is 17 out of 40, divided by just Y, which is 8. Sorry, yeah, 17 plus 8, 25. So that gives us, what did we say again? 17 out of 25. What is the probability of y given x? Seventeen out of 26, because you add the 9 and 17. Right? Okay. We need some variables. We need to create a two-way table. I don't know, men and women. What do you want to know about men and women? Just use your creative side. You have no characteristics, men and women. Teacher or not? Okay. Teacher, and if they're not a teacher, or a loser. Okay? I'm going to get in trouble for this one. Using such inappropriate language. Okay? Man and a teacher. Well, come on, there's something. Let's see. Women and a teacher, 11. Men and a loser, probably more. Yeah, 55. Probably going to go that big, but that's okay. Women and a loser, well, women are generally less losers than men. What do you want to say? 2. 2? All right.
Yeah.
All right. So in order to do this, we got to get our totals. So we got 20 teachers in this group and 57 losers. And of that, we have 64 men and 13 women. You would think the odds are good, but you've got 55 losers, remember. Anyway. I think I'm recording this too, so this is awful. This is terrible. But I'm just going. Just going. All right. What is the probability of selecting a loser? 57 out of 77. What is the probability of selecting a man or a teacher? Teacher or a man? Tom. So we could do this a couple of ways. We could say that there are 20 teachers total. There are 64 men total, but we subtract the overlap, right? That's one way. Or you could just say, okay, this is at least a teacher. This is both. This is at least a man. So we would include all those. So there's 2 ways you could do it. So we should get 75 out of 77. Okay? And the last, are the events man and loser independent? Do you remember how to do this? We need 2 probabilities, and if they're equal, they're independent. If they're not equal, they're not independent. So let's just find the probability of a man. What's the probability you get a man? And we want to make this decimal because we're going to have to compare the two. So 64 divides 77. 0.83. Okay, I'll put that. 0.83. And then we do the conditional. What's the probability of choosing a man given that they're a loser? 55 of 57. That doesn't look like it's going to be the same. That looks like it's going to be higher. 0.965. Okay. So we would say these two events are not independent. Okay. If they're equal, because then one doesn't influence the other, right? Like the probability of selecting a male is about 83%. However, the probability of selecting a male, given that they're a loser, is much higher. So that means whether they're a loser or not impacts the probability of a male. That's really what it comes down to. Okay, I think I've said the word loser enough.